Welcome back to the 8th installment in the series about capacitive liquid level sensing. In the previous video, we added a reference electrode here to our sensor to make our measurements independent from the dielectric constant of our liquid. However, our initial design for that reference electrode was not quite satisfying because the capacitance of that electrode slowly creeped up as we filled the container, instead staying at a constant level. So at the end of the previous video, we built an improved sensor. Card here, link in the description. And now let's see if that improved sensor really improves things. Enjoy! Short recap. Our initial sensor design with a reference electrode had the lead from the reference electrode running on the outside of the sensor. So the lead, a little yellow speck here, was going from our reference sensor here to the side and running up our ground plate. And we suspected that the capacitance of that lead was strongly influenced as the water level was rising in our container for the whole length of our sensor, causing a majority of that creep we observed. So, in version 2, we have now buried the lead to our reference sensor here under the ground plate, shielding it basically from the influences of the dielectric constant of our liquid. Let's test our sensor version 2 now, shall we? And again, I won't show you the process. I will do 25 milliliter increments, filling it up and taking the measurements. And I'll come back to you with the result. But we will do at least one live measurement during this video. I promise. Here's the data again from our sensor version 1. So when we first got a signal here from our signal or level sensor at 100 milliliters, we were at 49 picofarads. That was a delta from the air capacitance of our reference sensor of 5.5 picofarads. And then the capacitance slowly creeped up as we filled up our container to 54 picofarads. And that's an additional delta of 5 picofarads, or an increase to the initial delta of plus 91%, which was of course unacceptable. And that's the data from our new and improved sensor. As you can see right away, we reduce the creep quite considerably. It's not perfect, but we reduced it. So again, at the 100 milliliter mark, where we get the first signal here, that is a capacitance higher than air from our signal sensor. The capacitance is 59.5 picofarads. That's a delta to air of 49.5 picofarads. And then we slowly creep up 2 picofarads to 35.5 picofarads. So delta 2 picofarads, and that means only a creep of about 20%. Much better, but not perfect. But maybe good enough, so it's worthwhile to revisit our math and make it a little bit more universal. If you remember, initially we assumed that 5.5 picofarads at 11 millimeter capacitance delta on our reference as a constant. Of course, if we want to really be independent from the dielectric constant of our liquid, we can't do that, because the dielectric constant of our liquid could change while we fill up the container. Let's say it's a wastewater container. First we fill it up with some lightly soaped water, and then we fill it up with some really dirty water, and it mixes and it changes the dielectric constant. So Our initial math was only interested in the capacitance changes relative to the air capacitance of both our signal sensor and our reference sensor. And if you look at the second formula, you see we have here the capacity change in the signal over capacitance height, which includes the capacitance change of the reference. Let's write this more formally as the capacitance of our signal sensor minus the capacitance of our signal sensor in air over the capacitance of our reference sensor minus the capacitance of our reference sensor in air. Yeah, just looking at the deltas now. Then we divided, respectively multiplied the whole shebang by our reference height, that was 11 millimeters, the height of our reference sensor, and our volume per height factor of our container. Let's unify that to a single gain factor, effectively multiplying our delta signal over our delta reference with a gain. Please note, this is farad over farad, so this term is dimensionless. Gain could be in millimeters if we just want to measure the height, or if you have a container like that one where the height is proportional to the volume, gain could be in milliliters or in volume. Finally, we added an offset because our measurements due to the geometry of our sensor only starts at a certain height. So after adding the offset, which should of course be in the same unit as the gain and just characterizes when our measurement really starts on the signal electrode, we got our value, which could be, depending on what units you're using here, in milliliters or in millimeters. So either volume or height. That's how the math looks in an Excel graph. We've seen that before. So the green line is our actual fill level. So at 100 millimeter, 100 milliliters, 200 milliliters, 200 milliliters, etc. Then I took a gain of 67.9 millimeter, which I hand optimized. You could use mathematical methods of that, and an offset of 75 milliliters. The 75 milliliters, of course, because there our signal is still at air capacitance and then it starts rising. So we get, using our math, this blue line here, which is of course below 75 millimeters unusable, but starting with 100 milliliters, we get here something that's quite close to the actual green fill level. And red is the error, that's the scale on this side here, and as you can see, our error is between plus minus 20 milliliters. That's about 3 1/3% of our full scale of 600 milliliters. That's of course worse than the results we got in the 6th video, cut here, link in the description, where we had an error of, let's say plus minus 15 milliliters of full scale, so plus minus 2% of full scale, which was of course better, but please remember we still have a creep of 20% in our reference sensor. Before we put that math into a sketch and put my incoherent rambling so far to the test, let's talk a little bit more about further reducing that creep and thus increasing the accuracy. Geometry-wise, we could try to minimize the capacitive coupling between our reference plate and our signal plate. Remember, the signal plate is connected via a 2 mega ohm resistor to ground while we take our reference measurements. We could also try to minimize the capacitive coupling of the reference plate to the upper parts of the ground plate. Both would probably reduce the creep a wee bit. So if we take here all the copper that is currently rolled around my broomstick and flatten it out in a plane, it would look something like that here. So here we have our lone reference plate, and then with some distance we have our signal plate, okay? Less capacitive coupling. And then we could thin out the ground strip here, so there could be less field lines for going from the reference here to the upper part of the ground plate. And remember, we need still some ground plate here because the lead is of course going below the ground plate. Or we could come up with totally different geometries where the ground and reference and the ground and the signal plate are completely separated. The important part here is to minimize the capacitive coupling between the parts we don't want to be capacitively coupled. Of course, such geometry changes would inevitably lead to our measurement area starting even higher, let's say at 200 milliliters. And we don't want that, and so I won't build a version 3. Instead, we will try what we can do electronically to minimize our creep. Just as an experiment, let's try what happens if the signal plate is not connected via 2 megaohms to ground, but is dangling while we are taking our reference measurements. To implement that, I just added a few statements to my loop, more specifically inside my for statement here, where I do my measurements. So before I actually do a capacitance measurements of my reference, I set the signal drive pin to input. Make it, well, not really dangling, but high impedance. And afterwards, I set it back to output because I still need to drive my signal plate. And set it back to low and do, just to be on the safe side, a delay for the signal discharge time. And then I do the same symmetrically here for my signal measurement. So also here I set my reference drive pin beforehand to input, and then only after I did the signal measurement, my reference drive pin is set back to output. I set it to low and I wait for it to be discharged. Let's have a look at the results. And that did absolutely nothing. I have here exactly the same creep of a delta of 2 picofarads from 51.5 to 53.5 picofarads, and I'm still starting here with an air capacitance of 46.5 picofarads for my reference plate. Really, the only way I can visually distinguish that measurement from our previous measurement is that the bumps, the measurement errors in my signal electrode are a little bit different, okay? So there you can see it's not the same measurement I used twice to fool you. But yeah, absolutely no improvement. The question is, why? There are two reasons. First, the plate we are currently not measuring is not really isolated. The pins of our microcontroller, here the values for the ATmega4809 on my Arduino Nano Every, do have an input leakage current, which is typically below 0.05 microamps, which is very low, but it's still there. By the way, the values for your ATmega 382P on your Arduino Nano version 3 are maximum of 1 microamp leakage current. Meaning, while doing a measurement of our reference, we had an arrangement like that. Our ground plate was obviously still connected to ground, and our reference plate was still charging up via a 2 mega ohm resistor from 5 volts. But our signal plate was not isolated. There was a current source plus minus 0.05 microamps or whatever connected to it, either charging it if it was at 0 volts or discharging it as it was exceeding, let's say, 2.5 volts. Second, we have a very large capacitive coupling between our signal plate and our ground plate, which only gets larger as we fill up the container. And the capacitive coupling between our reference plate and our signal plate is probably small compared to that. So in fact, even totally isolating our signal plate would do nothing, because we could still have some charge here in the small capacitor to the ground via that large capacitance here. In conclusion, eliminating creep electronically is really the domain of specialized chips, and I will put a link into the description to this paper from Analog Liquid Level Sensing using capacitive to digital converters. And without going too much in the details, because that's outside the scope of this video series, you can see that both plates of the reference and the signal sensor are driven active. So, not really something we can do reasonably without external parts with a microcontroller. You can also see here in the electrode arrangement that they don't really care about capacitive coupling between the reference and, they call it here the level sensor, which we call the signal sensor. That's just parallel on their PCB, whatever, because they are driving both sides of both sensor actively. And at one point in the far future, we might talk about the chip they are using. That's the 87746. But again, not in this video series. So let's move on to actually doing some measurements in milliliters, finding out if everything really works as expected in the code. I added six new constants here. So I have here my float for the signal dry capacitance in picofarads. That was the 30.5. And for my reference dry capacitance in picofarads, which was 46.5. I also have here a signal minimum capacitance in picofarads. That's the minimum capacitance I consider viable for measurements. There is a little gap here between the dry and that minimum capacitance, just to account for noise. You will see the logic later on in the code. I have the same for the reference, so there's a reference minimum capacitance in picofarads, which is also just half a picofarad about the actual dry capacitance. And then I have here my conversion gain in milliliters, that was 67.9, and my conversion offset in milliliters, that was 75.0. In the loop within the for statement, I removed all the pin mode, digital write, and delay statements because they did nothing for us. But I added, after the printouts of our capacitances, here some statements. So first I check if our reference capacitance is smaller than our reference minimum capacitance. If that's the case, I print out dry. Otherwise, if our signal capacitance is still smaller than our signal minimum capacitance, then I print out low. So the reference electrode is kind of wet already, but we don't get a valid signal out of our signal electrode, so I say it's low. If both are above their minimum values, then I calculate, according to the formula I've shown you, the fill level in milliliters and print that out. And now let's put that to the test. So you see we have our usual capacitances here, and we print out dry, and yeah, everything is dry. Now let's fill that up a little bit, so to the approximately 50 milliliter mark. Did I hit that? Yeah. And now we get low. Great. Let's go up to 100 milliliters. Are we at 100? Yeah, we are pretty much at 100. And I can't decide if it's low or 80 milliliters. Let's give it a little bit more. It's hard to see. Okay. Now we're reading, and it says, yeah, 98, 97, 99 milliliters. We're a little bit above, but yeah, maybe 5 milliliters above. So little error there. Let's go up to 200. And I get these errors again. But it's okay. After it stabilizes, we would probably have to extend our discharge time a little bit. We're spot on to 200 milliliters. I mean, plus minus a few milliliters. That's impressive. That's astoundingly impressive. Let's go to 300. Okay, 300 spot on, and we're getting those error messages, and let's say 290 milliliters. So 10 milliliters off. Just 10 milliliters. This is working better than our specifically for water calibrated stuff. I'm a little bit flabbergasted. After the Excel numbers, I didn't expect that good of a result. Yeah, 400 milliliters, and we're at, yeah, let's call that 380. We're 20 milliliters off. That's what I expected. That was what the Excel sheet was showing. Yeah, 500. And we give it a little bit of time until it's settled down. We too much error messages, but it's only one error per 20 measurements so far. So we're a little bit off here. It says 400, let's say 470, 460, 470. Wiggling a little bit, that always helps. No, not. Let's say 470. That's an interesting effect. Okay, we have to extend the discharge time. But anyway, let's go up to 600. 560, 550. This wiggling around is making me nervous, especially why do we get so much discharge voltage to high errors? You won't believe what the problem was. The problem was that sorry, my big fingers are here, that the USB cable of my Arduino was running back there parallel to mains AC power cable for a while. And that put so much interference here in that cable that, yeah, that was measured actually. But anyway, we now got a nice result here. Well, not so nice, of let's call it 570, so 30 milliliters off. So yeah, an error of 5%. That's more what I expected. In between, it was eerily on spot, to be honest. Now let's prove if our little sensor with the right software can really do measurements independent from the dielectric constant of the liquid. As we learned in part 1, card here, link in the description if I not already carded it, that is. Water has a dielectric constant of about 80 or 78. While a saturated solution of salt in water has a dielectric constant of 32, so less than half. To get a saturated solution, you need 357 grams per liter of water at 20 degrees C. I only need half a liter, and that's 178.5 grams. So let's wait that out. And I'm already out of salt. No, not really. I have more. And I'm weighting ounces here. That was not my intention. Okay, grams. What did I say? 178.5. That's a lot of salt. 172, 5, 6, 7, 8. Okay, that should be enough. That's a lot of salt indeed. I mean, we're at about 125 milliliters by volume. No, 100 milliliters by volume. Okay, now let's add 500 milliliters of water. Yeah, that sound looks right. And now I stir and stir. I'll come back to you when I finished stirring and everything is in solution. Okay, round 2 with, saline. And 50 milliliters. Are we at 50 milliliters? Yeah, a little bit more. It says still low. Yeah, of course. So let's go up to 100 milliliters. 100 milliliters. It's still low. 150 milliliters. We're measuring 140. Let's say 140, and we are at 150. So 10 milliliters off. Let's go to 200. And we're spot on again at the 200 mark. Woo! 300. Spot on. Damn it. 400. Spot on. That thing, okay, let's say 390. But it's measuring saline better than pure water. Yeah, maybe I was a little bit lazy when calibrating the whole thing, huh? 500. Okay, and now at the top we get some errors. Yeah, otherwise, we're a little bit low. Let's add a little bit more. Yeah, 500. So let's call that 470. 30 milliliters error, that's within our 5% of full scale. And 600 milliliters, we are also at 500, well, 570, 580. So yeah, it's working. That's it for today. There will be at least one more part because today I don't have enough time left to talk about some itty bitty details like how I came up with these resistor values and the charge times, and why you should use really short leads and avoid coax cables, and yeah, a lot more. If you paid very close attention today, you also saw a very weird effect happening, and we will talk about that too. So, till next time, bye.